Thank you. Good afternoon, ladies and gentlemen. My name is Oddbjørn Gjerde, and it has already been introduced that I work with SINTEF in Norway, and I am coordinating GARPUR. An outline of today's webinar is now shown on the screen. I will start with giving a brief introduction to the GARPUR project and the philosophy. Then Louis Henkel from University of Liège will introduce the GARPUR methodology, and a case study for real-time operation will be presented by Samuel Perkin from Landsnet, which is the Icelandic TSO. Then finally, Louis Henkel will sum up, and we have a slot for questions at the end. So, to my introduction. The short version of present practice regarding transmission system reliability management is N-1. As you already know, the N-1 criterion refers to the ability of the system to continue operation and serve load even after a contingency. N-1 has been the cornerstone of TSO reliability management, and we believe it will be important also in the future, but it has some clear shortcomings or limitations. A major shortcoming is that N-1 will treat all outages as equally probable. Also, it does not distinguish in any way between different consequences of outages. It is not sufficient to deal with uncertainties in large, complex systems. And what about the increasing probability of multiple outages? Altogether, we see that there is a clear need for a probabilistic approach, which also will need to take corrective actions into account. GARPUR responds to this by making a framework to balance reliability and costs. The question is, how can we reduce socioeconomic costs and still maintain reliability of supply? For this, GARPUR has designed, developed, and assessed new probabilistic reliability criteria and evaluated their practical use with focus on social welfare effects. And for this, the different TSO time horizons are covered. That is power system operation, asset management, and also system development. The figure on the screen shows the outcomes of GARPUR in a very compact way. To the left, we have different alternatives or aspects of reliability management that should be taken into account. These could, for instance, be spatial temporal variation, utilization of corrective control, demand-side management and storage, impacts across the time horizons, and also low probability, high impact events. Covering these aspects, we are setting up a probabilistic reliability management framework, as indicated here on top of the figure. We also set up a socio-economic impact evaluation framework. These two frameworks are adapted to system development, asset management, and power system operation through TSO-led work packages, leading to our proposed new reliability criteria. Also, a quantification platform is developed for testing the new criteria towards N-1, and a roadmap for the deployment of the new criteria is being developed. And also, of course, dissemination towards stakeholders of the electricity market is important, just like here today. So, to sum up, GARPUR is creating a consistent, continuous and comprehensive framework and tools to balance reliability and economics. All time horizons are covered, resulting in a more optimal socio-economic impact or balance between reliability and costs. So if you need more information about the project, I suggest that you visit our website, garpurproject.eu, where you can also find information about our final conference, which will take place in October in Brussels. Thank you. And we can now move on to Louis Henkel. Please, the floor is yours.
Good afternoon, everybody. So my name is Louis Henkel, and I'm a scientific advisor of the GARPUR project. And I will introduce the methodology for probabilistic reliability management proposed by GARPUR. First of all, I will highlight a little bit the different weaknesses of the N-1 criterion, then talk about the proposal in a nutshell, and talk a little bit about its implementation in practice. So, well, the N-1 criterion, as I guess everybody knows, for instance, for real-time operation, consists of defining a list of contingencies, typically all N-1 events that have to be covered. And sometimes, of course, there are some additional N-K events included in that list if deemed necessary. And for each one of these contingencies, the system should be able to survive, meaning that the simulated response within steady state and stability limits has to be satisfied for each and every contingency in that list. And within this set of constraints, then the TSO can optimize an economic objective, which would be, for instance, minimizing operating costs, which are typically a sum of preventive and corrective control costs and also congestion costs. So let's look a little bit at this criterion by using an overall socioeconomic impact measure, which is a cost function summing up two terms, namely the total risk for end users, which is the expected socioeconomic cost of service interruptions as implied by all possible contingencies and all possible failure modes that can happen in practice. So not only those that are covered, for instance, by the N-1 criterion, but in principle all kind of events on the one hand, and on the other hand, the operating costs, which are all the direct costs of the TSO minus the induced market surpluses. So this is a sketch of the way one can view these two cost functions. In blue, we have the operating cost, and in red we have the total risk as a function of the set of contingencies that would be covered by the TSO in real-time operations. Suppose, for instance, the TSO applies the N-1 criterion, then this will lead to a certain operating cost, and there will be a residual risk because there are some contingencies which are not N-1, which still may happen, have a certain probability, and could lead to load shedding or other consequences which are monetized in this risk, which is the expectation of these values. Now, obviously, if you, let's say, apply the N-0 criterion, the operating costs will be much lower, but the residual risk, of course, will be higher. And if you apply the N-2 criterion, the reverse will hold. And ideally, what we would like to do is to operate at the optimum here where the overall socioeconomic impact is minimal, which is the sum of the expected cost of surface interruptions and of the operating cost. Now, while on this graphic here, it looks like n-1 gives a solution which is close to this optimum here. If we are in another situation, for instance, in a situation where there is a lot of available wind power and maybe suddenly there is a drop, then maintaining the n-1 criterion may lead to a very strong increase in operating costs. And so the optimum would then shift to the left of the curve here, meaning that in such a situation it would be more wise to not cover all the n-1 contingencies. And let's say similarly, if the weather conditions are harsh, then of course the probabilities of some of the n-2 events will increase, and so that the total risk of service interruptions will increase, and in this case the optimum of the overall socioeconomic impact will shift to the right here, and meaning that it would be wiser, closer to optimum, to cover more than just n-1 contingencies. So the general situation is that most often actually the n-1 criterion does not lead to an optimum situation from the overall socioeconomic impact. And so therefore we need an approach which allows us to basically adapt the set of contingencies to available information about all these curves. So this leads to the overall idea of the GARPUR proposal, which is explained in this slide here. In order to decide which subset of contingencies should be covered, we propose to dynamically adapt to information about socioeconomic costs of service interruptions, corrective control failure modes, and of course probabilities of contingencies and of these failure modes. Meaning that, for instance, if we are in a situation where there is an important event like G7 meeting, the cost of service interruptions might increase because we really don't want to have an interruption at that moment. Or if the weather conditions become harsher, then the risk of having multiple contingencies or single contingencies, these probabilities will increase or decrease depending on weather conditions. And the same for the possibility of corrective control failures. So this is the general idea, is to take into account all information that is available in a certain context to adjust in a dynamic fashion the list of contingencies that are to be covered. And this leads to a formal mathematical statement of a stochastic optimization problem that we call the GARPUR RMAC. There are 4 ingredients in this RMAC. First of all, the reliability target. This is a set of technical and possibly economic conditions that we want to impose on the possible system responses due to uncertain factors like contingencies, variations in load, and so on. And so we formally define what we call an acceptable system trajectory, and then we set a threshold on the probability of unacceptable trajectories. So we want this probability of unacceptable trajectories to be below a certain confidence threshold. Second part is, of course, to formulate a socioeconomic objective function which incorporates both TSO costs, market surplus, and the costs of possible service interruptions. And the third important ingredient is a principle which allows us to define in a dynamic fashion among all the possible contingencies, or more generally among all the possible things that can happen and with respect to which the TSO wants to cover himself, those that could be discarded, so don't have to be covered explicitly, so as to reduce, for instance, the list of contingencies to a smaller list, which is really those that carry the largest probability times the largest risk of service interruption. With these three parts, we have an optimization problem with some constraints. And this problem may or may not be a feasible problem. If the problem is not feasible, then we need to be able to relax it by dropping out some of the constraints. And so we also formalize in the GARPUR project how to relax the problem in any case where it is not feasible. Of course, these 4 components can be applied once we have models, which means a probabilistic model of the different threats like contingencies, variations in power injections, and so on. We have defined a set of candidate preventive and corrective control actions used for reliability management, and of course we need a physical model of our system like always. So to finish this part of the presentation, this graphic shows the different contexts in which we want to apply this general idea, so-called GARPUR RMAC framework, from long-term to mid-term to short-term and then real-time, and to cover both grid development, asset management, and operation planning, as Obion also already has explained in this introduction. So for each one of these contexts, we have to formulate an RMAC, and so we have to define the different ingredients that I have just explained. And we insist on making the long-term context decision-making coherent with the shorter-term context decision-making processes. So in general, we can say that we impose that longer-term decisions are chosen so as to enable the reachability of shorter-term reliability targets, meaning that, for instance, in operation planning, they had operation planning. The operator would then take decisions so as to make sure that over the next day, the reliability target and RMAC can be satisfied by the operator, given the uncertainty that is present the day ahead. So this finishes my short introduction to the general idea of this probabilistic approach developed in GARPUR, and I give the word to Samuel, who will explain the application in real time. Thank you.
Thank you, Louis. So I'll be, as Louis said, I'll be talking about how we can implement the ideas that Louis just discussed in a real-time setting using the Icelandic transmission system as an example. So the first 10 minutes will be spent showing how we can move from a traditional N-1 assessment to a probabilistic reliability assessment. And then I'll give an overview of how we've applied this to the Icelandic system and what we're doing differently with the pilot test, and then walk you through some of the initial results that we've managed to get. So to move from the N-1 criterion, we need to move from physical to probabilistic indicators of system states and of risk. So a traditional N-1 assessment will calculate the lost load and any breaching of operational security limits following a contingency. But to achieve a probabilistic reliability assessment, we need to convert this lost load into a measure of energy not served, which is lost load over time. And then we need to convert this into interruption costs, which is an economic measure based on the value of any service outages to end users. And then we need some probabilistic estimates for the likelihood of contingencies to convert this into a risk measure. And then we have some of the indicators that were raised by Louis that are kind of a system-wide reliability indicator. And in order to estimate these values, we need new models. So in order to estimate the loss load following a contingency, we probably need to upgrade our system response models in order to capture all the dynamics and system protections and also any corrective control that the TSO might employ. And to calculate energy not served, we need some model that converts the initial disturbance into a loss of energy over time. We need socioeconomic models, probabilistic models, and ways to aggregate the individual results for contingencies into system-wide measures. So the next few slides will walk through these steps to give you an idea of how we can achieve this in practice. And in order to do this, I'll be using the Icelandic system as an example. So I'll just be looking at the N-1 set of contingencies, which just consists of branch and generator failures. And I'll be applying the heavy loaded but full topology case, so no components presently out, and at maximum load. So in such a case, we have a number of voltage issues, which when applying corrective control, most N-1 contingencies result in a fine operating state and a few result in some potential load shedding. And so this is what we would expect from a typical N-1 contingency analysis. And if we rank these contingencies based on the expected loss load, we find that a particular contingency, number 99, seems more severe than the rest of the contingencies. In order to convert this loss load estimate into an estimate of energy not served over time, we need a model that predicts the service outage duration based on the severity and location of any loss load. Within GARPUR, we suggest a simple heuristic model because this is not something that TSOs normally model. But as you can see from the orange line, which is a simple linear heuristic model, compared with the black dots, which represent Landsnet data, these sorts of heuristic models aren't necessarily accurate. But at the same time, we lack data related to very severe outages. So in some sense, a heuristic model is always necessary for the most severe of cases. When we adjust the loss load estimates based on this heuristic model, we find that it just linearly scales the loss load into energy not served. And so the relative ranking of the contingencies is unchanged. And contingency number 99 still maintains the top spot. In order to convert this into interruption costs, we need some understanding of which consumers were affected by any service outages. So in order to do this, we have information of the demographics at each node on the Icelandic system. So a breakdown of for any load on that node, which types of consumers are using it. So commercial users, industrial users, or residential users. And for each of these user types, we have a value of loss load curve. So this tells us for some outage duration how much this outage will affect the different types of consumers. So if we look at the commercial consumers, for example, they're more affected in the first 15 minutes of an outage than they are in the 5th hour of an outage. And so the economic impact is very time sensitive. When we scale the consequences, so energy not served, by the value of loss load curves, we find that the relative importance of the contingencies changes. So the previous worst case contingency when using a classical N-1 approach is now relatively insignificant, whilst now one of the previously small insignificant contingencies seems to be the most severe. So in order to convert this into risk, we need measures of contingency probability. And as discussed earlier by Oddbjørn, these probabilities are not static, but in this case, we'll just use the average probabilities for contingencies in Iceland. So we find that one particular contingency on average occurs 0.04% of the time. And there are a few other high likelihood contingencies, but in most cases they're quite low in likelihood, and the worst contingency in terms of interruption cost is quite unlikely, as you can barely see next to the 100 on the figure. If we then convert the interruption cost into risk by multiplying by probability, we then find that a new contingency becomes our most severe event, and that the contingency number 99 that we discussed earlier seemingly disappears off the map, and the worst contingency in terms of interruption costs still maintains some importance. So the first insight that I can give is that by applying a probabilistic socioeconomic-based reliability assessment, we find that we should defend ourselves against different sets of contingencies. So if we'd taken measures to defend against the worst contingency, number 99, in terms of N-1, we would find that we wouldn't actually affect the risk state of the Icelandic system so much, and that instead we should be taking care of this blue contingency over here. Finally, we need to aggregate these risk measures into the aggregate measures discussed by Louis. So the assessed risk is simply a summation of the risks of the individual contingencies. So in this case, it's around 9,000 krona, which is roughly equivalent to 70 euros. And the residual risk is the risk associated with all the events we didn't cover, so the N-2 contingencies and all the higher order events. And in this case, we assume that they would result in a blackout. And so if we assume the blackout costs essentially 5 billion Icelandic krona, and we calculate the discarded probability as 0.001%, we find that the N-1 assessment on average has a residual risk of 68,000 krona, which is equivalent to 500 euros. And in order to affect this residual risk, we either need to add more contingencies to our contingency list or discard them, as mentioned by Louis earlier. The final measure, which is the probability of an acceptable system state, that first requires that we define what an acceptable system state is. So in a classical N-1 approach, we aim to have a system that complies with our operational security limits. So it's most intuitive to consider those to be our acceptability constraints. So to calculate the probability that we will end the hour in an acceptable state, we simply take the probability that no contingency occurs, and we add that to the probability that any contingency results in an acceptable system state. So in this case, we calculate 99.5% of the time we expect to be in an acceptable state, which is equivalent to being in an unacceptable state 40 hours of the year on average. So if we wish to move from N-1 to GARPUR, in addition to the additional tools and calculations that I've just gone through, we also need to include some variable failure rate models, so models that depend on weather and other threats, as well as the vulnerabilities of grid components. And from this, we need to develop some variable contingency lists, which are based on a contingency discarding tool that I think Louis will cover later. We also need to use real-time system state data and real-time weather data if we wish to use these models in an operational context. And we also need to take into account any unexpected scenarios, so changes in intermittent generation or changes in load. The interruption costs that I showed are also just one aspect of a full socioeconomic impact assessment. So we haven't considered in this example things like operational costs or environmental costs, but they should, within the context of GARPUR, be assessed. And finally, the aim is to not just assess risk using probabilistic approaches, but to be able to control the risk by suggesting control actions that reduce the overall risk state of the system while still complying with the acceptability constraints. So for the Landsnet pilot test, we've achieved the first three of these points in addition to the models that I walked through earlier, but we're yet to cover the points shown in red. And the general methodology of the pilot test is that we read in the latest snapshot of the system state every minute, and then we pass this into a useful format. And we also read in live weather data to then calculate live failure rates. And these are just based on wind speeds at the moment. And then given the live failure rates and the live system state data, we apply the 5 modeling contexts described earlier in our probabilistic risk assessment. And then we update some temporal outputs and create some visualizations for the end user. And in doing this, we try to maintain the same residual risk as in the N-1 case. And we also keep our contingency list to 5,000 or fewer contingencies in order to ensure that it calculates every 2 minutes at least. So the main output of the pilot test is a web-based user interface that provides live reliability information to control room operators and anyone else who's interested in the company. And I'll go through some of these figures now. So the main figure is the risk curve, which is primarily sensitive to weather and hence to contingency probabilities. And you'll note that these figures at present on the screen, they relate to a storm. So there's a storm passing over the country between 14 o'clock and around 8 o'clock the next day. As you can see, the probability that we comply with our operational security limits decreases during the storm. You'll also note that there's a step in the risk function here, which is due to the economic models changing some assumptions due to the end of a weekend. So it's just reducing or increasing the impact on particular consumers depending on what the time of the week is. And so the probability that any fault occurs increases during the course of this storm. And as a result, the size of our contingency list also increases over the course of the storm. So before and after the storm, we find our contingency list is smaller than the N-1 contingency set. But during the storm, it increases by a factor of 10 in size. We also display the acceptability of the system in terms of MSOE event classifications. So we can determine that during the storm, most likely if there's any unacceptable state, it will just be a noteworthy disturbance. But that there is a slight chance of extensive incidents with a negligible chance of any widespread or major incidences. And we also, for debugging purposes, we've also been displaying the live wind speed data on a map. And a typical output that's created by contingency analysis is a rank of contingencies from most severe to least severe, such as in this figure. So we could rank contingencies from highest risk to lowest risk, and same from highest probability to lowest probability, and most loss load to least loss load, where risk is simply something of a multiplication between these two figures. But as you'll notice, such a figure is quite difficult to interpret because the appearance of a contingency here or here doesn't necessarily imply any particular position in terms of risk. So to try and resolve the difficulty in interpreting such a figure, we developed this type of figure. So this is meant to be animated, but it's not. That's no problem. So we have contingency probability on the x-axis, and we have estimated interruption cost on the y-axis, and then risk contours, which is just simply a multiplication of the two axes. And each of the top 10 contingencies is shown with an individual colored box. And so over the course of a storm, when the risk increases and then decreases, we might see that one particular contingency shifts to the right due to its probability of occurrence increasing, which would cause the risk to increase. And we may also see some contingency move upwards due to some additional congestion or load on the system, causing the consequence of such a contingency to increase. And so if we imagine these boxes moving to the right, leaving a colored trail behind them, we can then display all of the aspects in the previous figure, as well as the temporal aspects of how the state of the system is changing and how the risk on the system is changing. So to close this section of the talk, we've shown how, in a basic way, we could move from an N-1 reliability assessment towards a probabilistic reliability assessment. And we've also shown that such an approach is feasible on the Icelandic system, which, although it's small, it's a good first step, simple example of how such an approach would work. And it allows us to assess the best ways to scale such an approach up to larger transmission systems. And finally, most of the future work is related to capturing the dynamic stability issues on the transmission system, to improving our system restoration models, and to try and move from a risk assessment to some sort of risk control approach. So now I'll hand the presentation back over to Louis.
Thank you. So I will summarize the main benefits of the GARPUR approach, which are listed here in this first slide. And so first of all, concerning the contingency selection, as you have seen on this example shown on the Icelandic system, we have developed a principle, which we call the discarding principle, for choosing the subset of N-1, N-2, N-3, etc. contingencies that should be covered either by preventive or by corrective or by combination of both type of control actions. And this allows to select and to adjust the set of contingencies that has to be covered in operation to, for instance, weather conditions, but also other conditions which have an impact either on the probability of contingencies or on the cost of service interruptions, basically. And this principle should allow operators to adjust their perception of the risk and determine a strategy to manage reliability in a more dynamic fashion. And so this is justified from a socioeconomic point of view, since basically what the discarding principle says is that we should take into account all those contingencies that might have a significant impact on the overall socioeconomic impact, including TSO costs, congestion costs, but also service interruption costs. Then the second step, we have talked mostly about real-time operation, is that we also have developed in GARPUR a systematic approach to define reliability management approaches and criteria for longer-term decision-making, coming back to the day-1 problem. When you want to decide what to do 1 day ahead in time, what you have in front of you is uncertainty about the consumption and generation pattern of the next day, and also, of course, about the weather conditions, and so also about the failure probabilities and so on that will happen. Nevertheless, what you can do is see how the system would be operated in real time along a set of possible trajectories for the next day, trajectories which are then sampled according to your uncertainty that you have about these factors. And for each one of these trajectories, you should basically look what would be the response of real-time operation in terms of reliability management, and see whether or not it would lead to problematic situation where the residual risk would be too high, or the probability of unacceptable system response would be too high. And then this allows you to assess day ahead different candidate decisions that you can take in terms of the implied risk on operation. If you go further in longer term problems, like for instance asset management or for instance outage scheduling, which are problems where you typically look over a period of several months ahead in time, then you would wish to choose how to schedule your outages in such a way that they would have a minimum impact on system operation, including day-1, day-2, and real-time operation. So then, let's say if you consider that one of these Russian dolls represents the real-time operator, if you are day ahead, you have to incorporate somehow a model of the real-time operator in the decision-making process. And if you are in the midterm, let's say a few months ahead in time, you have to incorporate actually the sequence of finer-grained models from, let's say, day-2 or week ahead to day-1 to real-time to emergency mode. And so in order to make this kind of problems tractable, of course, we have to simplify these ways we are modeling shorter-term processes, and we have introduced a notion of proxy to formalize this in the GARPUR project. We also have, in the project, worked in a coherent fashion on the two complementary aspects of reliability management, namely reliability assessment, where you want to see whether or not in a given situation the system would be sufficiently reliable over a certain horizon, and reliability control, where you want to find an optimal decision in terms of socioeconomic impact, making the system sufficiently reliable over a certain horizon of time. And these two parts, of course, can be used in combination in order to help operators to manage reliability in a more efficient manner than they can do today by taking into account these probabilities and cost of service interruptions in their criteria. And we have also worked in the GARPUR project on a simulation framework which allows us to study offline the impact of moving from N-1 based reliability management to the probabilistic approach by simulating over a set of scenarios both how the system would perform when we would use the N-1 criterion on one hand, and on the other hand when we would use for the same exogenous conditions the probabilistic approach. So this should allow us to compare the type of decisions that would be taken with the two families of criteria, and to see also the impact on the actual socioeconomic performance of the system when using either the N-1 or the RMAC. The idea is to use this simulation framework to better understand how the method, the new method works with respect to N-1, and so help TSOs to progressively adopt this approach in real operation. And so for the next webinar, we will talk about this aspect, which is what we call the GARPUR quantification platform, which allows us to do such simulations, and we will present how far we have been able to go with the development of that platform and also of its testing. Finally, there are other pilot tests which are being carried out for the time being, and they will be presented as well during the next webinar. And so where we'll also, for instance, discuss what it means to use the probabilistic approach for long-term grid development studies. And so this leads me to conclude our presentation and open the floor for questions. Thank you very much.